All right, let's dive in. Today, we're going to put on our detective hats and investigate those super frustrating electrical faults. You know the ones, the mysteries that can stump even the sharpest technicians. And I'm going to show you how to crack the case by looking for clues where you'd least expect them.
I mean, we've all been there, right? You're chasing a ghost in the machine. You've got a sensor that tests perfectly fine, a circuit with perfect continuity, but the problem just keeps coming back. It really feels like you're missing that one key piece of the puzzle, that vital clue that would make everything just click into place. So, what's the big secret? Well, here it is. The solution to so many of these electrical mysteries isn't buried in some complex wiring diagram. Nope, it's in the big mechanical system that all those wires are attached to. The engine itself, that's the key. So let's start our investigation. Okay, so if we're going to be detectives, we need a crime scene. And for us, that's the engine. To find the real culprit behind our electrical fault, we have to know this scene inside and out. It's time to start gathering some clues. Our very first clue is all about the physical layout of the engine. Think about it. You can't possibly diagnose a system if you don't even know how it's physically bolted together. This is all about knowing the lay of the land from the very top to the very bottom. So let's just trace the whole mechanical stack. It all starts at the top with the timing belt or chain, which is like the orchestra conductor for the camshafts and valves. That whole assembly sits right on the cylinder head, which is the cap for the engine block. Now inside that block, you've got the pistons and connecting rods doing all the heavy lifting. And way down at the bottom, the crankshaft takes all that crazy up and down motion and turns it into the smooth rotation that spins the flywheel. It's just a beautifully precise piece of engineering. And here, right here, is where the mechanical and the electrical become one. That crankshaft position sensor you're testing, it's not just floating in space. It's physically reading the teeth on the flywheel. That ignition coil, it's bolted directly to the camshaft cover. So before you can even dream of testing an electrical part, you first have to know exactly where it lives in the engine's physical landscape. Okay, so we've got our map of the crime scene. But a map only tells you where things are, not what's happening. To really get what's going on, we need to see the engine in action, moment by moment. And that brings us to our second clue, the operational cycle. This is the absolute heartbeat of the engine, the four-stroke cycle. It all starts with the intake stroke, as the piston moves down, taking a deep breath of air and fuel. Then comes compression, where that mixture gets squeezed under incredible pressure. The power stroke, that's the moment of truth. The spark plug fires, igniting the whole thing and driving the piston down with explosive force. And finally, the exhaust stroke pushes all the used-up gases out, clearing the way for the next cycle. Intake, compression, power, exhaust. It's this furious, perfectly timed dance that's happening hundreds of times every single second. And this right here is exactly why that cycle is so important for us. When your scan tool spits out a number for ignition timing, what does that number actually mean? Well, it's meaningless without the context of the compression and power strokes. A cylinder pressure reading is just a random number until you know for sure you're testing on the compression stroke. The cycle provides the context that turns raw data into a real diagnosis. So, we've seen the engine's anatomy, we've watched its actions. Now let's look at its identity card. Our third clue is hiding in the numbers, the key specifications that define an engine's unique personality and how it performs. These are the fundamentals, right? The bore is just how wide the cylinder is. The stroke is how far the piston travels up and down. Put them together and you get the engine's total displacement. But out of all these numbers, there's one that completely changes the electrical game: the compression ratio. This tells us exactly how much that air-fuel mixture gets squeezed. And believe me, it has massive implications for the electrical system. Just look at that number, 22:1. That is a typical compression ratio for a diesel engine. That's more than double the 9:1 we might see in a standard petrol engine. That means a diesel is squeezing the air with more than twice the force. And that single difference sends a massive ripple effect through the entire electrical system. Because these numbers directly control electrical behavior, that insane 22:1 compression ratio means the starter motor has to work incredibly hard just to turn the engine over. So when you do a starter current draw test, knowing that high compression ratio tells you to expect a much, much higher amperage reading than you would on a petrol engine. The mechanical spec literally sets the electrical baseline. Okay, we've gathered our clues. We've got the anatomy, the cycle, and the numbers. Now for the fun part. It's time to do some real detective work. We're going to connect these clues to crack the case. And the key is understanding the massive differences between petrol and diesel engines.
This slide really lays it all out. A petrol engine, it uses a spark plug to ignite a low compression mixture. A diesel engine, on the other hand, uses the intense heat from extreme compression to ignite the fuel. No spark plug needed. So what does that mean? It means a petrol engine has a whole complex ignition system, while a diesel needs glow plugs just to get started when it's cold, and it needs a way beefier battery and starter motor to overcome all that compression. Electrically, they are two completely different worlds.
And this is the critical takeaway. If you go into a diesel engine bay looking for a distributor or an ignition coil, you're not just wrong, you're wasting precious diagnostic time. Trying to apply the rules from one system to the other is pretty much the fastest way to get lost and make the wrong call every time.
So, let's tie it all together. Every single major electrical system is directly and functionally linked to the engine's mechanical operation. You change the ignition timing, you change the power. The starter current completely depends on the engine's compression. Even the charging system has to work harder as the engine's speed climbs. You simply cannot separate them. They are one deeply interconnected system. So, what's the ultimate lesson here? It's simple, really. To become a true expert in electrical diagnosis, you absolutely have to be a master of mechanical context. The real clues aren't just in the wires and the sensors. They're in the cast iron, the pressures, and the fundamental cycles of the engine itself.
By understanding the engine's anatomy, its cycle, and its core numbers, you're no longer just a technician swapping parts. You are a diagnostic detective. You now have the framework to solve any electrical mystery that comes your way. So the only question left is, are you ready to start solving?